with the set theory. Again, a review of set theory. So we're not defining sets, and we're not attempting to define elements of sets either. So we just assume that we know what that is. We define sets as lists, as what I mentioned last time, and as well as we define them by means of a property. So x in R, x greater than 0. Okay, so which may or may not be satisfied. If it's satisfied, then x belongs to the set. If it's not satisfied, it does not. So that's all there is. Okay, so and that is a starting point of a lot of set theory, and we didn't do really a lot of set theory if you think about it, and there's a reason for it, because it really doesn't make sense to start from in such an abstract setting without actually seeing the reason for why we want to do it. So early on, if you pretty much have nothing but calculus to look back to and see where set theory might appear, it might be not enough. So that's why we introduce things such as a little bit of topology, a little bit of algebra, in order for you to see to have experiences outside of calculus, and now every time what appears, every set theoretical concepts appear. Another place where we did not talk about, and that's also a very good place for set theory, is combinatorics as well as probability. Okay, so I hope I mentioned a little bit of that today. So let me just refresh your memory about very simple things, such as from set theory. Once we know what the set is, the idea of a set, then we do algebra of sets to begin with, right? So everything is introduced in a set theoretic way, through typically this is a way more common a way to introduce a set is through property. So you have if you already have sets, to form new sets, you indicate properties. So relations will be subsets. Remember this: subsets, intersection unions, complements. So these are the four would be the most basic. So subset. So A is a subset of X. F. So this is the definition. X belongs to A implies that X belongs to X. Okay, this is the definition. Our definition of a subset. So that is one way to put it. Another way to put it is well, you can speak if you speak of properties. That's to be satisfied for A and X. It means that one property is more restrictive than the other. Okay, so once again, they're like x greater than 0 or x greater than 2, right? So then one is a subset of the other. X greater than 2, right? It will be a subset of x greater than 0. So less restrictive, more restrictive property. That's subset. And then we start form A intersection B very explicitly x and x, assuming that everything x is the universal set. That's either you call it the ambient set, you can the universal set. It means that all the computations with or operations with sets you're going to be doing, you're doing with all those sets are subsets of X. Okay, so it is kind of restricting your attention to something that we know is a set. If you have a set and then you take all of its subsets, then it might be a lot enough for us to do everything we want, but as we know, if we go too far broadly, then we might end up with sets that are poorly defined and might behave badly. That's the example we looked at yesterday, right? So the Barber's paradox, the Russell's paradox, the ones that might be problematic. One is also when we run into trouble with set theory if we just try to do too much. Think about the set of sets, the set of all sets. You take the set of all sets. Is it what is it? Is it a set? You take all sets and then form a set of the sets. Is it a set? And then once again you can ask yourself, if it is a set, then it should belong to itself, but on the other hand, it's not on the list of sets, so it's not a set. Is it a set? So it's such a monstrosity that you usually just don't, you never use it, but how do you make sure that you don't use something that can get you in trouble? Well, this is one way to do it. So just make sure that there is one that is a set, is the one that we can handle with set theory, and then and at least within that universal set, everything is fine. So that's the best we can do. It's not like there is a way to around those problems that I just pointed out last time. So there are logical issues to deal with, and they cannot be easily resolved. So that's best we can learn from the history of foundations of mathematics and the crisis, in fact, what's called, of the 20th century. Okay, so I just point out the limitations of set theory and logic too. Okay, so and we continue doing set theory in this naive way, and as the word sounds pretty bad, but actually everybody does it. That's no way around it. So, and we start forming new sets from old sets in this manner. So intersection x, those x belong to x, that x belongs to A, and x belongs to B. Okay, there you go. Or union x in x, such that x belongs to A, and or x belongs to B. Okay, so in that manner you can define sets. You can define the complement, right? X in x, x does not belong to A, like this. So we have formed three sets. Okay, based on these, this is not actually the end of it. The unions intersections are not a binary relation, or a binary operation rather. You can have infinite unions, as we talked about when it came up in topology. So a union of more than not just you go 1, 2, 3, 1 by 1. It's like algebra. Carry out one operation to the second operation, and then you have as many as you like. But that will never give you infinitely many. Okay, so specifically, for example, if is it possible to take the union of, say, 0, 1, well, what I have in mind, 0, 1, union 1, 2, union 1, 3, union. Okay, is it possible can we make sense of such a union of infinitely many terms? So this cannot be carried out by in consecutive operations. So can we make sense of this? What is it? Zero, 1, 1, 2, 1, 3, I'm sorry, 2, 3, 3, 4. What do you end up with when you put those all together? Well, you can make a picture, right? So 1, 2, 3. Makes perfect sense. If I just this is 0, 1, and then 1, 2, 2, 3, 3, 4, on and on. Okay, so it does not end. So the end result is what?
I mean, we get all real numbers.
Yes, starting from 0, real numbers, yes. Okay, so that example is just meant to point out that there is really nothing wrong with taking a union of infinite many sets. There's, even though, so it's not, which makes it kind of, you realize that's not really algebra. when you do 2 and you do union intersection, that as we have done throughout the semester, unions, intersections, and their complements, and they interact with each other as if it is algebra, and it's very interesting. But really, there is if we have infinitely many, it's not as obvious that it doesn't seem as algebraic anymore. So how do we define a union of more than 2 elements? Well, first the notation. So what we do is we define a set of sets. So what is a set of sets, specifically subsets? So that makes life easier if we have one universal set, and then we do unions or intersection or whatever of that set of sets. So the idea starts with so that's just let put it aside for a moment. What is a set of sets? The starting point is just a set of all subsets. It's called the power set of X is the set of all of its subsets. Is denoted by px usually. All subsets right there. So we have formed a new set, which is really nothing is kind of big. It is kind of big, considering bigger than X. Okay. So for example, let's take a few examples of this. Say if my X set is 1, 2, what are the subsets? Let's list them. 1, 2, 1, 2, which is X, and at the end, the other end is the empty set. That is, by the way, is very nice, that notation that I like for the empty set. I like it, but I never use it actually. But look at it. So the empty set is denoted by list with no entries. So every subset is ultimately every set and every subset is a list. Okay. So what if that list has no entries? That's an empty set for you. Okay. And then sort of as you can see, it fits in the pattern. So a list of one list of one element followed by the list of 2 elements. These are the 3 subsets that actually have something in them, and then there is one. We want to list all of them. Okay, so we end up with a 0 or with no entries. That's the empty set. Okay, so that's just notation. Okay, so that's an example. You can imagine what happens if you go to 3. X 1, 2, 3. So empty set. So you can classify them by the number of elements they have. So it will be 0, only 1. Then you can choose one element subsets 3 ways. 1, 2, and 3. Then you can choose the 2 elements in how many ways? In how many ways can I choose 2 elements out of 3? Anybody has taken any combinatorics or probability? Although probability.
Not yet.
Okay, well, we'll just do a little bit of that in a minute. So it's, as you can see, it's about counting. It's very much about counting the probability. It's elementary, and it's where it actually started. You know, counting your odds when you're playing cards or any kind of gambling. Okay, so counting the number of outcomes which you win or versus how many times you might lose. All the possibilities, and that's what this is about. So to begin with. So I'm listing all possible outcomes, sort of. If we're picking a subset, let's pick a subset from a set of 3 elements. Okay, now I wanna list them in order to at least to count them. Okay, so one of them is, it's very easy to see that I can pick 3 elements one element out of three ways. In how many ways could I pick two? Three, right? Why three? Because the order doesn't matter. We are speaking of subsets, so the order doesn't matter. In 3, 1. Okay? And there is only one way to choose three elements. Okay? So that is a list of all subsets of element of three sets. So no infinities to worry about, but the concept of a power set is very important. And let's do just a little bit of counting. How large is the power set? How large is the power set? If for finite sets, that is. So we don't have to worry about. We'll review that later. But about the cardinalities. Cardinalities of finite sets is simply the number of elements in that set. So as you can see, what we have, so this is 1, this 0 elements, 1 element, 2 elements, and 3 elements. Here that classification was here as well. But the total, as you can see in the example of 1 element, the power set of X of 2 elements was 4, right? The first example, the cardinality of the number of elements in the power set of 3 elements is yeah. For some reason I put it 3, 3, and 3, 3. I was counting the numbers at the bottom. 0 plus 1 plus 2 plus 3, and it looks like 6. That's not right. So the answer is indeed 8. And that might suggest a pattern. Of the number of elements in the power set. When we had 2, we had 4. When we had 3, we had 8. What's the next one? 4.
16, 12.
Okay, let's check. So you can do it this way, by the way, like this. Okay, so there will be one of it, so 0, 1, 2, 3, and 4, okay? Still one choice here and one choice there in the beginning and the end, only one set that has 0 elements, okay? Only one element contains all elements, okay? How many ways can I choose one element? In how many ways can I choose one element out of 4? The answer is 4. What about 2? 2, 1, 2, 3, 4, 5, and 6. Okay, and how many ways can I choose 3?
4.
Yes. Can you explain why? Or did you count?
Yeah.
1, 2, 3. Which one did I miss?
Top left corner.
And 4, like this. So it looks awkward because it is, but it is actually easier to count. This is not a coincidence that one element choosing 4 times or 3 elements 4 times, because you just choose which one to omit. Right, for the line of choosing 3 elements out of 4, it's the same. Choosing 3 elements is the same as to choose which element to omit. So that's why the choosing 1 element out of 4 or choosing 3 elements out of 4 is the same number. Okay. So adding up. I'm sorry, this doesn't belong here. It is, who said 16? It is correct, 16. So 16. And so then we can guess if I have n,
It's 2 to the n.
2 to the n power. Yeah. So, okay, theorem. If the number of elements in a set X is n, then the number of elements in a power set of X is 2 to the n. Okay, so practically speaking, I mean, when you start, if you were whatever you're taking a probability course, it would be question related to this question is you have say a group of I don't know, you have 5 people and you want to form in how many ways can you form a group of smaller group out of 5 persons? Okay, and the answer will be 32 ways, depending on the number. If you know how many, so for the how many ways can I choose a group of 3 out of 5? So better, they always have the question like that. You have a team of 20 players, and you have to choose 5 to play basketball. And how many ways can you form a group of 5 players out of the team of 20 players? So that is not going to be the whole thing. It will be these rows that we looked at. Okay, so there's a combinatorial formulas for that to find out. You might remember with factorials. Anyone? Yeah. So there are formulas for that. If you want to choose if the number of elements or players is specified, then the choice is also there is a formula. And so we found one of the simplest formula of pretty much the simplest formula of probability theory or counting theory, finite. Obviously, so we're not going to go deeper into this, but let's prove it though, and the proof is kind of educational, I suppose, because it is that doesn't fit exactly into what we have been doing. So the trick is not to do what we did over there, classifying and explicitly counting. So even though it is clear that some of the things will repeat themselves, so there will be once again if you start with, there will be once again in the beginning and the end will be 1 and 1. Okay, so so in the first column is how many elements I want to have, and then I count how many ways I've got it in the second column. And so there's only one subset with 0 elements, and there's only one subset of 1 element. And now, but if I progress on to how many ways can I choose 1 element, and the answer is n. How many ways can I choose n minus 1 elements? Once again, n. We decide which one to omit, right? Which one to omit, and then there are a bunch of elements in between. Can you guess about the pattern? What's happening? It goes 1 and in the end it goes n1. What's happening in between? It will grow, and then it will go up, and then it will go down, right? So somewhere in the middle, there is the maximum number of ways you can choose the number of ways which you can choose that. So say the biggest number of, if you have a team of 10 to choose out of 20, that would be the biggest number of variations. And you might also remember where this, you may have seen the Pascal triangle. That's it, once again. So that's where everything comes. So if you, except it goes down rather than the way I did it, it goes to the right. But the computation is fairly straightforward one. We have an idea, not computation, but the proof. And that is just realize that every element of Px corresponds to, so I'm talking when we say corresponds to, is always, we mean exactly always the same thing. It is one-to-one correspondence. And it is a string of n zeros and ones. Okay? Every element of a power of the power set corresponds to a string of n zeros and ones. So meaning that we list our numbers. So entries 1, 2, 3, n. So these are my elements of x right here. And then I put here 0, 0, 1, 0, 1, 1. What does it mean? It means that 0 means that it is excluded, and 1 means that it's included. Included. These elements are included, say, here, n over 2. And these are excluded. So the idea is that about every element of the set, we have to decide whether it is, we take it or not. That's how we form subsets. We don't have too many choices. Every set, we look at it and we ask ourselves, is it in, is it or not? Is it in or not? Right? There are no variations. So it's we then put 0 or 1 against that number, that element of our set. Okay? Right? Any issues with that transition? So in other words, if we use the language of previous developments, and so we can speak of the number of elements of the power set, and the how do you know the number of elements? The same as if there is a one-to-one correspondence, or also known as a bijection, between these. And what we're talking about is here is so say E1, En, where each Ek belongs to 0, 1. It's not Z2, but because we're not going to do algebra with it, but this is simply the set of 0 and 1, and we're choosing zeros or ones. It is a binary idea, certainly, even though we're not going to be doing adding or subtraction or multiplying here. So once again, a string of n numbers, but these numbers can only be zeros and ones. And so it is the same. My power set, whatever that nature of x is, it doesn't matter. It corresponds to the set of all strings of n numbers when these numbers are zeros and ones. So then remains to be seen how many. So count these. Okay, so count these. How does that work out? You just you choose one by one the number of the number of ways you can choose each of these numbers. Okay, and there are how many ways can you choose every one of these numbers? 2 ways. So 2 ways to choose each of these. So 0, 1, two choices, right? And then you realize that is important for here, and probability it is to watch out for that the choices are independent of each other. So independence of choices is crucial. So that goes when you do counting. Obviously, you don't want to. If they are dependent, then you will be double counting things. So if one choice of the first has something to do with the choice of the second, then you have a problem with your counting. They have to be independent, and that translates into independence of what? Of random events. Okay, and that is when they are dependent, those random events, the word is correlation. Okay, and so if you are not realizing that those two events are related, you are messing up your analysis. For example, you're trying to, I don't know, you're investing into things, and you wanna you're investing into something, and you wanna make a safe bet. So what do? You spread your investment in two that are, then you do, if this loses, then this one will not. So I'm hedging, right? So, but the assumption is that they are not independent. The assumption they are independent, that's why if this drops, this one has no reason to drop in price, and so you are safe. But if they are related, then when this drops, this will also drop. Okay, and so you are not protected from this risk. And that's what they say. Some of the financial crises happen in many ways like that. So that hedging did not work because things are either explicitly or implicitly or obviously or non-obviously correlated, and they behave sometimes or often in the same manner, and then you're in trouble. So, but where does that thing starts? And certainly you pile up a lot of things on top of this little thing, but that little thing is at the bottom of everything. So you might be double counting things if there is a relation between these two. This is obviously is not. So we're choosing is not related. So you're choosing one, you choose the other. You can form any set that you like, and then it means that we are fine choosing two choices for each. Two choices for each, and then and that's where 2 to the n comes from. Why? Because if you choose 2 for the first one, so 1, 2, 3, and you choose twice, and then what's left is independent, and so 2 times more for the next one, and 2 times more for the next one. Every time you choose, you will have free choice of 2. Of 2, 0, or 1 for that element. You can do it inductively. This is induction. If you want to go into details, well, very frequently that's what happens. The idea itself does not have to be inductive. I mean, the idea is inductive. You don't have to do technically proof by induction if you understand the proof as it is. But you can do it inductively, right? So we already have a base of induction, right? So let me close this up. So this is equal to 2 to the n. Okay, so you can see that we have already a base of induction right there. So 2 to the n is true for n equal 1, 2, 3, 4. Okay, and then how do you expand? Suppose we are here, right here. We have 4 elements. How do we progress to 5? Well, we know how many ways we can choose these 4 elements. We're adding one more element, the 5th element. And that is the element we have to choose. How many choices we have? We have 2. So if we had 16 choices for a set of 4 elements, we add in one more element with 2 choices. We multiply the whole thing by 2. Okay, there you go. And so you have then 32 every time multiplied by 2. That's the inductive idea that here on display. Okay, so that's one thing that a nice property of power set of a set. Okay, so it is totally counted. Everything is accounted for by this formula when it is finite. So let's take a quick look at power sets when the set is not finite. Well, one thing to notice actually, it was noticed a while ago, that whatever that 2 to the n is, one thing is clear, that it is larger than the set itself, strictly larger. The power set is strictly larger than the set itself. Even if you have one element, how many subsets does this set have? A set of one element, how many subsets? 2, right? The set itself and the empty set. Okay, so it's larger always. So now what if x is infinite? Okay, is it still true? It's a good question. The answer is yes, but even to answer that question, so yes meaning that it will be larger every time. The power set will be larger than the set itself, always. Even though we are talking about infinite sets. We cannot, however, answer this question without properly setting up the question. And how do we set up the question to this? So the question is the power set larger then the set when the set is infinite. We have to set it up properly. How do we do it? Remember how we did it? What does it mean, larger, smaller, for sets that might be infinite?
Countable?
What?
Countable or not countable?
Well, that is in a particular situation. So you have a hierarchy of sizes, and that's starting with finite, 1, 2, 3, 4, and and then at the end is countable, and then beyond it might be uncountable. But that's not cover all the possibilities. And then, well, but you can certainly notice that it would be interesting to notice that what is a power set of a countable set is strictly larger than the set, which means that makes it uncountable. So that certainly is something that it's not something that we are discussed that. Remember, integers versus real numbers, right? And that was proven by the diagonal argument that one is larger than the other. And the number of real numbers is larger than the number of integers, or rational numbers for that matter. But the point of this question, the way I put it, that we need to review this part of set theory, of how we in what sense and how we can speak of sizes of sets. How do we speak of sizes of sets? No recollection? When we spoke of cardinalities, how do we speak of cardinality? What is a cardinality? How do we compare cardinalities of sets?
Inequalities?
No, so there are two sets, x and y are sets, then the cardinality of x is the cardinality of y if what? What's the condition?
If you contain the same number of elements.
But when it's finite, yes. If it's infinite, we cannot attach a number to it. In fact, we're trying to find a way to attach anything to the size of a set which is infinite. How do we compare? Okay, here's a hint. A hint is one word. As always in set theory. First, sets. The second one, functions. So the way to handle is with functions. There is function, which is what kind? Is it quadratic? Maybe trigonometric? What?
It might be like 1-to-1.
1-to-1 and onto. Or in other words, a bijection. A bijection, that's what creates compares the sizes of two sets. Okay, so we did it. If you it works perfectly well for finite or infinite sets. So let's go back for a moment and see where are those bijections. Well, here's one. The average element of a power set, which is finite. This is entirely discussion about entirely finite. So we have a power set, and then we put it in a correspondence, aka bijection, with strings of n elements of zeros and ones, Okay, so that's one example. Whereas everything here, this is the list. Listing things also works out. So 1, 2, 3, 4, 5, 6, 7, 8. That's the correspondence between power sets, the power set listed, and the numbers between 1 and 8. Okay, so that's a bijection, one-to-one onto function between the two. It is not worthwhile to insist on that terminology or set theory at all. If and you don't hear a lot of it. If you do finite things and you talk about, say, probability, then you won't be dealing with terminology such as bijection or a power set. But it is important when you deal with sets that are infinite. Well, I guess one thing I want to do emphasize that always comes up is that there is such a function. It doesn't mean that every function would be a bijection. So remember that counterexample is it means there's always a function. There might be a function that is between them that is not a bijection, even if that function is one-to-one. Okay, so one-to-one. Well, let's analyze this definition slightly. So bijection is one-to-one onto and onto. Okay, so let's make sense that both of these conditions are necessary. Just to take this apart a little bit, why do we require both of these? And why do we require that there is rather than for a? Okay, so we have to, let's see, what if we drop one of these conditions and let's think of functions that are, or other sets that are not, would not be considered of the same size. So a function that is one-to-one, clearly, if you just pick one-to-one and you drop onto, so no example, no onto requirement. Well, it's uncomplicated. Take a function f from one element set to, say, integers. Okay, so what? It is one-to-one, but it is not, by no stretch of imagination, you can think of these two sets to be equal. In fact, I could just take a set of two elements, just to keep it simple. Such a function that compares two sets has to be onto. Otherwise, you're comparing sets that are not, obviously not of the same size. Okay, so even with finite ones, it's not working out. If I drop one-to-one, then I can you think of a reason why one-to-one is necessary? Why this definition does not make sense if there is no one-to-one condition? Well, you can go backwards. Right, that doesn't well, it's obvious what the function is. So 1 goes to 1 and 2 goes to 1. The function is onto, but it's not one-to-one. And once again, it cannot, such a function cannot serve as a comparison between the sets. It is more complicated when you look at infinite sets, and this is the standard example of point out what the problem is. It is the function from even numbers to even numbers to the integers. Okay, so on one hand, you can simply go, well, let's say f of n is equal to n. That could be 1. F of n is equal to n. The domain is the even numbers, but the range will be also even numbers in that sense. So even though it is a function between even numbers and z, it is not onto. So this one is not onto. Okay, so that's why. So that function is useless. And if I want to compare instead, I'd say g from even numbers to z. Say same thing. If I want to compare the size of the set of even numbers with z, what do I choose as my function? I wanna. So this one is not onto, so I discard it because of that. But if I do want to satisfy my my definition, and you already know that the size of even numbers is pretty much the same as z, so there is somewhere, there must be, and you should know what it is, a function that bijection between them. So what's the bijection?
N divided by 2.
N divided by 2, that's right. N divided by 2, as you can see, it is it requires proof, obviously not hard, but still you should be able to do it. From even numbers to the integers, and you do cover all the integers all of a sudden, so it's like so it's say 0, 1, 2, 3, 4, 5. So these are my even numbers. If I pick the even numbers, then these are the ones. Okay, and then I don't know, and then across of it I have my z. So this is my z, and then I could go just straight across, and that will be, but that would not be onto. So what do I do in order to create a one-to-one function? I divide by 2. So when I have the 0, 1, 2, 3, 4, 5, my arrows of my function g will go like this. Like this, so they shrink. So you're shrinking the spread. Even numbers they are spread out through this set of z. Okay, and then you create a function that shrinks that function z, and then it becomes one-to-one onto, and then that's how we know that these two have the same cardinality. Okay, so so that's how we do it. So we'll just a bit more review. I guess this is a part that deserves a review, and that is a little bit more about sets, a bit more about functions. So one-to-one, separately from onto, together, bijections, and stuff like that. So we'll do it next time. Okay.